So you can see we did microgravity university, and we did all these radiation tests and electronics, rotisserie, a whirligig dispenser. We 3D printed these whirligigs of different designs, brainstormed all the different shapes that might be able to re-enter the very fringes of the Earth's atmosphere and spin to stabilize themselves, and have a little sensor on board and a little battery, and come into the atmosphere and radio some data back to the mothership as they're coming in. Has anybody ever seen the movie Twister? The old movie Twister? So you know these little gizmos got sucked up into the tornado, right? We did exactly the opposite. Instead of having them come from the ground up into the tornado, these came from space and came down. And we dispensed 6 of them. Every one of them was a different shape. We got back 0 of them. They all went into the ocean. Actually, some of them burned up, I think. But this is an example of what we set up. It's whirligig. So, and this is a model of one of our satellites. This is not the actual one, but this is the size of a CubeSat. This is the real size. This is not a scale model. This is the real size. If I backed up one slide here, you can see in the upper left-hand corner, there's the actual satellite, and this is the model for it. Now the one in the middle there, you can see some solar cells on this particular one. The one in the middle was 3 times this size. It was 3 units, and it had a boom that came out and solar panels. So we really encourage the students to be creative and design these projects and build them themselves. They don't always work perfectly. Some things don't work, some things do, but it's a learning experience. That's what's important, right? The learning experience. So we have problems with things leaking when they hit the ocean. You know, it's hard to make a watertight box, and it's hard to make a boom deploy and come back in again perfectly, but it's a lot of fun trying. Let's see what else is in this box. This is actually the little carrying case that we use to carry the satellites in when we go through the airport. It has the NASA stickers, and it has the NNU sticker. And it's amazing what TSA does when you carry one of these in. They're very interested because they look a little bit like a bomb or something. So one of the satellites that we built, MakerSat 0, is a very special case. It's 3D printed on the space station. The space station has a 3D printer in 0G. So we worked with the company Made in Space, and we 3D printed pieces of the satellite, structural pieces, on the space station, and used them. If you look at that little model that you're passing around, those 4 white plastic edges, corners, are the pieces that were printed on the space station. I mean, not that one, but the one that's in orbit. And it was snapped together and deployed from the International Space Station. So this is like a snap together model car kit that you did when you were a kid, or model rocket snapped together, really quick build, except it was a snap together satellite that's still orbiting, and it's still sending data, which is really cool. So I'll pass these around. These are the corner rails that were 3D printed. How to build a satellite in space. This is we put together a little YouTube video that you can look up under the word NNU MakerSat, and it was for the ISS astronaut team. It's like step 1, do this, step 2, do that. Basically a guide for how to snap together a satellite. That was pretty fun to create that video, and to, after you snapped it together, then you charge it. By the way, that's the 3D printer right there on the space station. It looks like a microwave oven. And you can see those 4 rails right there. Those 4 plastic rails, that's what's being passed around in the bag. So then this is a picture of the 3D printer printing the parts on the space station, the NNU parts. And then after they printed them inside this printer, then they floated them. This looks like they're outside the space station, but they're not. They floated them in the cupola window of the ISS so that they could make a nice picture. They also floated our logo, which they printed. This is the NNU logo. So it looks like it's in space, but it's actually inside the ISS. And that's pretty cool. We got those parts back, and there they are, back at NNU, with a cool box that was packaged right on the space station that said, "Critical space item." Hey, good to see you. I didn't know whether you'd be back or not.
Oh, yeah, I didn't have to come back, but I wanted to be.
Yeah, thank you for coming. Thank you for helping my class. I really appreciate it.
The same again.
So this is the way the satellite looks when it's laying. This is called the flat sat. This is the flat sat. It's like flower petals. The 4 flower petals lay out here. On the motherboard is in the center with Texas Instruments microcontroller running it. And you can see the battery pack and the radio up in the upper corner there, right in here. And so this thing folds up together and snaps together into a secure package, and it was deployed, and it's deployed on February 1st of 2020, so it's not quite been in space for 2 years. And traveling 16 times around the Earth every day, just like the astronauts that just got back, the new SpaceX astronauts. So you can see the boards were made here in Nampa. They were made partly at NNU and partly at Plexus. If you look closely there, you'll see the Plexus logo on this board right here. But all designed by the students. There you can see the Northwest Nazarene and the Plexus. This is like a part of the cube snapping together here. And when it's all snapped together, that's what it looks like. The flower petals have come together. It's ready to charge. You can see there's 2 antennas, transmit and receive antenna on top of the satellite. And it doesn't actually transmit directly to Nampa. It transmits to the network of satellites called Globalstar. And so the data goes from this little satellite to Globalstar, and then it's transmitted to a ground station, stored on a server, and then we get it back. So that's pretty cool. There's the final picture. And that poor little lonely satellite, who's got hold it up in the air there. That poor little lonely satellite is just floating around Earth all by its lonesome there. So that's the way it really behaves. We wanted to do some cool science on board this thing, so we said, what happens to 3D printed plastics? Who's got 3D printed plastics? Here, hold those up. So that particular material is very unique. We used ABS, which is really cheap, and we used PLA, and we used nylon.
Excuse me, Steve, what does ADS stand for?
Yes, what does it stand for? I'm not sure I can pronounce it, but I know you can. Say it again. Whew. All right. So that's a pretty cheap, generic plastic, not meant for space flight, and it's really not UV resistant. UV is intense, right? No atmosphere at all. So this is very UV resistant. It's called Ultimet. It's a mixture of polycarbonate and that's not the name of it. Polycarbonate and that's not PMMA. I'll think of it in a moment. But it's really robust for UV. So we used that plastic to print the pieces of the spacecraft so that they would hold up to UV. But we didn't really know. NASA didn't know either. NASA had this experiment orbiting outside the space station for 3 years with different types of plastics. None of them 3D printed, just plastics. And you can see that some of these samples, when they came home, were completely missing. The ionization and all of the effects of space actually slowly eroded some of them completely away. Making your satellite out of that material would be a really poor choice. It's like it just disappears after a while. So we wanted to know which type of plastic would be the most robust for building this little satellite out of. And you can see there's ionizing radiation, outgassing, atomic oxygen, plasma erosion, all kinds of things, even micrometeorites that hit the plastic. So we built this little board. It's like a drum head, and it has cantilevers on it, little cantilevers like diving boards. And at the end of the diving board, on each of the little diving boards, we put a different sample of 3D printed plastic, different types. And then we had a motor to vibrate the whole thing and run through a whole range of frequencies. We could change the frequency, basically testing for the resonant frequency, right? We were scanning for the resonant frequency of each of those cantilevers. They all had different resonant frequencies because they all had slightly different masses at the end of the diving board. And in fact, the mass at the end of the diving board was eroding slowly because of space over time. So we could watch the frequency slowly change on each of the materials, and they did not behave the same. All the materials behaved differently. So this is a cool experiment. We got to publish this several places, including a big national conference where one of our students presented to 5,000 people at one time. It's better than I did for. You can see some of the resonant. You see the basically like a pinging, a tuning fork. You can see the waveform here in response. This is taken from space. This is space data, and we plotted that and got resonant frequency changing as the mass went down slowly over time. What's happening to the frequency as the mass is going down?
Frequency increases.
Frequency is going up. Does that make sense? Less and less mass if you put a light kid on the end of the diving board versus a really heavy guy. So that's what happened in space, and we were able to measure that for each plastic. And the winner was what you have in your hands. Whoever has it, it's back here, I think. So it was Alton. And now the 3D printer on the space station is capable of printing that material. We also did a radiation experiment looking at radiation in space with the Caldwell High School team. Mr. Dennis Zatiro's high school electronics team did a particle counter looking for radiation particles flying through the auroras. This spacecraft happened to be a polar orbit, so it was going through the North Pole and the South Pole. How often? 45 minutes between the two poles. So every 45 minutes it was going through the polar region. It still is, 4 years later. So you get an aurora very often. And so we could measure particle counts. Also, there's another, you know, the Earth has 3 poles, kind of, sort of. The North Pole, the South Pole, that's kind of obvious. But what about this pole right here in the South Atlantic? There's an anomaly in the magnetic field of the Earth, and it affects satellites that fly over. It affects all kinds of things. It basically sucks radiation in at that area of the South Atlantic, which could do a lot of damage to aircraft and spacecraft that are flying through there. And that anomaly we detected also with our satellite. So you can see the team doing a little high five action here. I love these moments. Engineers should have one of these about every year. If you can have one a year, it keeps you going. One high five moment a year. That's what we live for. So this is just some of the testing. We tested the satellite. You can see the little box here that I was telling you about that I carry in here. But we tested the satellite on the roof of the science building in a cake carrier. You know a cake carrier? Now, why did we do that? Why did we use a cake carrier? We wanted because it was delicious.
Yeah.
We wanted some sunlight to get to those, so it had to be translucent or transparent. But what about leaving it just sitting on the roof of the building?
Somebody probably walk off with it.
Well, they couldn't get to the roof, but something else could walk off, could fly off with it. What about birds in Nampa, Idaho? Maybe even pooping on it on the roof? Okay, that's not good for your satellite. So we wanted to protect it, and we tested it in a cake carrier for days and days up there. You can see a vibe table here too. In the upper left-hand corner, that's one of our students, Brayden, putting this on a vibe table, vibing it for pre-launch at different frequencies. This is Ben working it. Notice he's working with a ESD jacket. Oh, you know Ben very well.
Yes, I've hired Ben several times.
Yes, and he's got his gloves on, right? He's got his ESD jacket on, and he's got his wrist strap to an ESD, so we have to make sure everything is taken care of so we don't fry the satellite. And you can see the pieces here that we've talked about. He's holding the actual satellite. This is the model right here. And this is one of our students, Brayden, with his family and his girlfriend, who is now his wife. And he's holding another satellite. There's his little brother, who I think is also going to be an engineer someday soon.
Did you tell them what Ben's doing now?
Ben went directly in May from NNU directly to graduate school at the University of Alabama, Huntsville. He is studying for his PhD in aerospace. He might stop with a master's, but he's in the program. He's doing propulsion at the Propulsion Research Center that's right next to NASA Marshall Space Flight Center and Redstone Arsenal. And he gets to work on a new NASA project which is called Nuclear Thermal Propulsion. And it's really a cool project. It's just funded by NASA, so really happy for him. I think he might end up being the second astronaut from NNU. He's determined to get himself positioned to apply for the astronaut corps, and I'm determined to help him. So, and again, this is Brayden and his family. They're from Melba, and Brayden grew up on a farm in Melba, and he's launched 2 satellites in his college career into orbit as the lead mechanical designer. He's now working for an aerospace company, doing great stuff. It's a startup company called Visioneering, and life-changing, right? Went from a farm in Melba, 2 satellites in orbit. His whole career and life has changed. So anyway, we'll move on past this. This is what it looks like when you pack satellites up for the space station in this dispenser box loaded with slingshot. It's called slingshot, like David and Goliath story from the Bible. The slingshot throws the satellite into space. So this is the slingshot. It has a big spring in it. There's 3 satellites in this picture. 1 large one and 2 small ones there. The NNU satellite is this one right here in the corner. And you can see the students working in the clean room lab. This is at Cal Poly San Luis Obispo, where all of the CubeSats are prepackaged before they go to NASA. And then after that, this is the NASA staff taking the dispenser and loading it directly onto the rocket. And then there we are. This particular launch was at Vandenberg. You might know where Vandenberg is, on the coast of California, down by Santa Barbara. This was launched from Vandenberg. You can barely see the rocket back there in the background. That's as close as they would let us get. But we're there. There's the rocket for that launch. Pretty exciting. It was a nighttime launch. And there's our team celebrating. That's not celebrating the launch, that's celebrating the deployment. You can actually see Ben there again. And this is a student from Caldwell High School who was a senior in electronics class, seeing his experiment going to space as a senior in high school. So anyway, that's the current status. The bottom line is it's working well. It's traveled a lot of orbits, and we did it again. The next time we launched was not on a NASA rocket from Vandenberg, but on a SpaceX Falcon 9 from Kennedy in Florida. And we got to be there as close as you can get We drove right to the foot of the launch pad with Falcon on it. And it was alive. It was, before the launch, the thing was alive. It was making sounds, and it was rather intimidating to be at the foot of the rocket with it making sounds. And then we came back for the launch and watched it from the roof of the Air Force Space Squadron Administration Building, which is on the, this is called the Cape Canaveral Air Force Base, which is just south of Kennedy Space Center. So we watched the launch there, and it was spectacular to watch the return. The picture in the upper corner here is the Falcon 9 first stage coming back down, preparing to land, and it landed just a little ways away from the launch pad, delivered its payload, came back down. 7 minutes later, we were waiting there. It broke the sound barrier, came in and fired its engines. This was before it fired its engines, and landed just perfectly on its tripod legs. Just amazing, amazing. You can see the landing right here with the tripod legs.
By the way, you guys, we're having a gentleman come in here, his name is Bill Keane, who designed the retro fire rockets for that push the nitrogen out, allowed it to set down gently. He's gonna be in this classroom here soon.
What's his name again?
Bill Keane.
Here's some of the teams that I've described, those students, and then there's our cool. Now I want to show you one more slideshow here if I can get to it, and it should be on the. It's not a show; it's a single slide. Let's see. Here he is right there. It's going to be pretty busy. Let me make it as big as I can.
Question back to this.
Does anybody know how to? Anybody know how to get out of this mode? Just tell me how to back up to full screen mode from this.
Try display settings up in the middle.
Right there. That'll work. Thank you guys. This just tells you about our heart for mission work around the world, not just space projects. I can't bring mission work with me, but I can tell you about it and show you some pictures. And we've done projects from 2011 all the way to 2021 every year in Peru, Africa, Papua New Guinea, Argentina, Liberia, Myanmar, and this year in Kenya. And actually the newest one just started today, this morning, and it's in Guatemala. So all of these have engineering hardware, really important designs that affect the lives of people. The project in Guatemala that started today is a tilapia farming enterprise for poor Guatemalans to actually not only feed their families, but to have income by growing tilapia fish in a small aerator tank that they can afford to build there. And so we're working with a team down there to do tilapia farming as an enterprise for families. Last year's project is this elementary school that we're going to install in May of next year with solar and Starlink internet out in the middle of nowhere in Kenya. And that project is really cool. And then we've done just different projects over the years that are what you see in every case. It's a lot of happy engineers, very fulfilled engineers, with a lot of lifetime friendships made with people around the world that they're still Facebook friends with, that they understand their life better, they understand their needs better, and it's a lifetime kind of commitment. So, not every student gets to do this, but every student that wants to do this gets to do this at NNU. There's other students that do corporately sponsored senior projects as well. And I think I'm going to tell you, stop there for a moment and ask questions, but I got one more handout. What time do we have to get out of here? All right, let me stop, and you can ask me any question about the research projects that you saw in ag or space, or the mission projects here, just anything. Yes?
How does that, since it's a phone block factory, where do they get the material?
For the foam block factory.
Yeah.
So that was in Peru, and fortunately, the capital Peru, Lima, has construction materials, polyurethane foam ingredients that they ship in from China. So it was available to get the two ingredients to make polyurethane foam in 55-gallon drums. One 55-gallon drum of chemical isocyanate, polyol, and isocyanate. Those are the two chemicals, and we shipped them in directly from China to Lima to the outback in Peru. We put together a truck, flatbed trailer that had a generator on it, diesel generator, and the spray machine to mix those two chemicals together and spray it. And it had rebar and cement and a few other things. And basically we could pump out these meter-sized blocks. There's a little girl there with a stack of blocks around her. They're like meter-sized blocks. They weigh 1 kilogram and they're a meter. You could throw them up to the top of the scaffolding, and if they come back and hit you on the head, no big deal. Or you could make a stack of them and make scaffolding out of them and stand on them. They're strong enough to stand on. So then we stack those up, pour them full of cement, and build churches and buildings. And so 20 churches were built around Peru. And then they moved the system to Ecuador, did the same thing in Ecuador. And then there was an earthquake in southern Mexico a few years ago, and they needed some rapid response for building structures after the earthquake, and they moved the system